Good morning, this is Dave Kroll. We're here with another episode of our Simulation Masterclass series. We have today Doug Shannon, who is a senior modeling and simulation engineer with GreenDart. He developed performance models for weather satellite sensor data retrieval and ground data processing measuring vehicle data latencies, data reliability, and sensor ground data processing capacity for the National Polar Orbiting Operational Environmental Satellite System and the Suomi National Polar Orbiting Partnership Programs. Also, we have Richard Marymee, who is a lead systems engineer with GreenDart, specializing in space system and launch vehicle modeling and simulation, responsible for creating a system simulation of a proposed defense weather satellite system architecture. Richard was the interceptor flight kinematics lead engineer for most of his 15 years working on the ground-based mid-course defense system, previously known as the National Missile Defense System with Boeing Defense Systems. Previous to that, he supported the DoD working with program managers on quality engineering for naval weapon systems in Corona, California. And with that, I will transfer things over to Doug and Richard.
Good morning. Thank you, Dave. Richard, you're on the line?
Yep. Good morning.
I want to thank Richard for all his help in getting our presentation to the Winter Simulation Conference in Washington, D.C. in December. And there we talked about rain attenuation. And that's about as exciting as it sounds like it would be. Part of what was in the presentation was simulating loss of rain and recovery. And so we'll be looking at polar orbiting satellites, which was just a small piece of our paper. And we'll be looking at data loss and recovery somewhat, and a great deal at ground processing. I want to thank GreenDart for hosting Richard and I as we went out to the Winter Simulation Conference, and we'll hear more about that. So we're looking at polar satellites today. We'll be looking at the model behind it. We won't actually take you block by block on how to build a polar satellite model, but we'll show you enough of what Extend can do that I have to believe you can go build it yourself if you know the possibility is there. We'll look at sensor data retrieval, ground processing, and Richard did all the support work in rain attenuation and the satellite toolkit. Richard?
Yeah, good morning, everyone. Again, my name is Richard Marymee, and thanks again to Doug and Dave. And if you look at the screen, you should be able to see the animation now for the SDK portion of what we are working on here. We created a little animation, actually, a scenario using 3 fairly generic satellites for representing a weather satellite system. So that's kind of the background for both Doug and myself in this realm here. So I use Satellite Toolkit basically to create these 3 little trajectories for a sun-synchronous type, sun-synchronous type satellites in 3 orbits, about 98-degree inclinations, about 850 kilometers altitudes. And what we did is we used the ephemeris data from that to do our analysis on 3 different receiver sites. So we looked at Svalbard, McMurdo, and Guam. Svalbard and McMurdo are both near the poles, so for a polar orbiting satellite, obviously you're going to get a lot better conditions there, a much more likelihood of passes and such. But we looked at Guam specifically because we wanted to look at the case where we would have loss of data, and we used the rain attenuation issue as part of that just because that was a good starting point for that, although it could represent other things such as jamming or EMP effects or solar flares or whatever you have that might interfere with your data transmission, because that's really what we're talking about here today. We basically use this as the setup for that, and as part of that we also included the effects of rain attenuation and how that increases with decreasing elevation angle. Doug, I don't know if we wanted to talk about that now or later on, but I could talk about the elevation effects right now.
We will get back to rain attenuation, but
okay.
It is a key attribute to point out. We'll soon, there are only about 4 charts before we get into a tour of the model, and we'll be looking at the Extend model down here, lower left-hand corner. Richard pointed out we have some near-polar ground sites in Svalbard and McMurdo, and Guam is of interest because we picked it as one that would have rain and we could lose data. We wanted to lose data, not what our normal goal would be. So we have those ground sites. We have a detailed data processing model. We'll keep it at a high enough level, but we'll be in the model shortly. And just to tell you, the data loss and recovery that was the key aspect of a paper we gave in Washington, as I mentioned, Richard and I. And there's the paper. So if you really are keen on modeling or representing rain loss, that's definitely where you want to go look. The paper does cover how we took 10 years of historical data and boiled it into a representative model for rain in Guam, how we would lose that data and how we would recover that data. As I said, the second portion of the presentation is in the model. We'll be looking at how the weather model ground processing and data flow is modeled. One of the concerns I had in looking at the attendees is that we not only have NASA, NOAA, and other aerospace companies, and they're definitely going to be interested in orbital modeling and how data communication fits in orbital modeling, but we also have process flows and ground processing on the ground. So I wondered if the manufacturing and industry, the participants and attendees in that realm wouldn't find or would find of interest the fact that we will be flowing data through multiple processes in order with dependencies and resources required. It's a very good data processing model, and it could apply to industry and to commerce. One thing about this kind of modeling, it's to take a paraphrase Lance Armstrong, it's not about the data, it's really how you illustrate the data, how you illustrate the environment that generated that data, that brings your customer from a pie chart and table presentation into your model and understands the value of your data and understands that you have a background for the data. As I say, we have aerospace and we have industry out there, and I asked Dave for a couple of surveys. One thing I would like to find out would be the area of interest you have in terms of the orbital decommutation and type of things that we are looking at in this model. Dave, do you have that chart you can bring up? Okay. Later on, we will get back to the audience and find out how many of us are experienced with Extend, and perhaps this is a new touch on how you might model orbital simulation. Certainly, you would start with something like STK to get the orbital bodies and provide that data to Extend if it's all about modeling the environment. Is the poll out there?
It is, and looks like we've got 65% voted, so I'll wait until that number stops clicking up. And
so all they can see is that poll at the moment.
Yeah.
So later on we'll also find out if anyone in our industry and our audience is doing flow modeling, and if that flow modeling has touched upon data communication modeling.
Okay.
Data communication model you'll see today is all about a discrete event model, a series of millions, thousands of packets kind of shown in the bottom of a chart that you will get back.
Okay, I've got
poll down?
Better than 90% response rate, so I'm going to close the poll.
Okay. So what do we know?
So we had 10% was orbital model, 43% was data communication, and 62% was data processing software and hardware architecture.
That's very respectable.
I can
Nobody's
share
moving
that
jammers
result
out
there with everyone.
Okay. Well, it's good to hear that there is an interest in the audience for ground processing. You'll see something that's done very little, seldom done very well, and that's processing data or any kind of data flow in the ground in a representation that tells you and tells your customer that you understand their system. Let me know when my screen is back.
Okay, you're
sharing
back.
Still? Okay, so I think with the next chart, Richard touched upon this, and the idea of doing this is to produce data for your customer, and you'll see how we do that in a very visual way. It's about data latency. You're collecting data worldwide with weather satellites. It takes a while to get the data stored on the spacecraft and downlinked to, say, these 3 receptors we've shown, and that we're going to lose data. We're going to have accountings for how much data is lost, how long it takes to get the data to the ground and processed. Things you'll want to trade in a simulation like this, or trades and alternative orbits, where to put your ground stations, shown in this first bullet. And I may put on a pin. Second is reasons that you might lose data would be your we mentioned jammers and weather, solar activity. But if you are losing data, the question is how do you get it back, how quick do you get it back? And there are schemes that we were looking at back in the IMPOS days to never lose data. So recovery schemes or loss avoidance is certainly an issue. Then in that, this model has a very good ground architecture for processing data or flow of data. We were able to look at alternatives for minimizing latency, what might be ways to maximize your performance, and for any customer we've worked with, it's all about cost. Way to prioritize the data, look at other processors, maybe to analyze the way you put your data flow together. So I have to get rid of the pin. Hold on. So with this, I will escape into a demonstration. The model is currently running. There are a number of things I can show that are available to everybody as soon as you open the model. What we're looking at on the top half of the model is a Mercator map showing the orbital performance of 3 satellites. Okay, the spacecraft in the upper right-hand corner, we've got 3 flight bodies, and you can see them flying right now. And so I've been collecting 25 hours worth of data. We'll be looking at what goes on board the spacecraft in terms of data. We'll be visiting the satellite recorder. Now this is a perfectly new block that if you wanted to build yourself, you would have to go to Wolves and Sheep. Is that right, Dave? It's a one of the example models in, pardon me?
Yeah, the wolves and sheep model has a similar data representation in there.
So this is an extrapolation of that model, went in and made it applicable. What you're looking at in each one of these color bars, and we'll get into it later again, is the contents of a satellite recorder for the Defense Weather Satellite 1, 2, and 3. And right now I'm showing weather data that is in the satellite recorder. As it is being collected, there is, for each of these satellite recorders, 1,500 data points being represented in a color map. To make this interesting, to make it relevant, right now they're plotting, hopefully you can see a color. Nobody out there in black and white, I have to believe. That if it's red, the satellites, I'll pause right now. The satellite number 1 in yellow has just passed over the equator, and you can see its color map is red. The red one has passed into the moderate zone, it's gone to green, and you see the green satellite is recording data over polar. Now this isn't weather satellite data, this happens to be a representation of its latitude, and that's a way to show where the spacecraft is, and latitude is certainly data that we use. And what I put into that recorder and what I display, since we have about 4,500 data points, can change. I can switch over to ocean and land, so we'll see it change. On the left-hand side is the Mercator map. Down below, we'll get into it a little bit later, the ground processing, the ground segment. We'll come back to that later. We'll see how data flows through it. And the weather model in Guam. By the way, you'll see the icon for the weather map change. Right now it's sunny in Guam. This doesn't mean you should go check Google to see if it's sunny in Guam. This is a representation. What we have is enough realistic data over 10 years of collection to have sun in Guam followed by periods of rain. And later on, we'll have rain in the model and we'll lose data. That should be exciting. The model, the Mercator map, everybody has this ability to plot data with a worm plotter. You can see the ground tracks for the worm plotter showing where the satellite has been, and you can see the leading edge. What's available in the model to you in Extend is that you can actually change and put in different maps as a background. So we're using a Mercator map, and we've centered it on Guam because we wanted to show loss of data. 1 second while I clear the ink pen, which is always there. So let me see. I'm in the Mercator map. I'm collecting data, so we'll visit what's going on with the orbital model. It's a good model, and the reason it's a good model, it runs fast. It is importing data from STK. This is the lat long data that Richard spoke of. When and if we're over a ground site, You can see the line of sight contacts. All this information is imported from STK. We have run in past a connection with STK interactively, and that's a much different model. We have used STK as a display. Certainly what you have here in a Mercator map is data points every minute shown on the plot. STK would give you a very high-res model. So we have done interactive displays with other tools. Let's see, another thing of interest, when you see satellites, and there's still 3 of them, entering an area, in this case McMurdo, you'll see content from McMurdo going up. And the reason we can do that is Extend allows you to put blocks. Here we have a satellite block laid in behind the map, and so the animation from that block is showing the amount of data as all satellites cross path with McMurdo. So I'm going to do a few things to speed it up, and then we'll go back to look at a few things. I'll just turn off this satellite. We'll go down to 2 satellites. We've been processing ground data. Let's see, why don't we do something fun here. I'm going to break McMurdo, and this is just a model I put together in a number of weeks, and it could be done admittedly a little better. But if this is still running, we should have 2 satellites flying. All right, be nice to see 2 satellites flying. There's 1, there's 2. I've turned off McMurdo, so the amount of data in all the satellites, and I've turned off 1 satellite, is going to have almost a full orbit before it can get back to McMurdo. And that will impact a lot of things going on in the ground. So I'll leave it run that way a little bit. Let me see what my notes say. So there have been modifications to the Mercator map. I modified the extend code, which is open source. I made it from a worm plot of 2. I made it to a worm plot of 4. And I also made a change to the code that would refresh the screen every 100 minutes so that my ground tracks would clear up. As I said, we modified a modified code that was used for the wolf sheep, and hopefully we'll get better renditions into this in time. But this is a color map that can be changed, and essentially all it's doing is plotting contents of the satellite recorder, which is being filled in by another block, and it's periodically giving me status by plotting here on the screen. Okay, I'm going to turn McMurdo back on because it does play a role. So the next time we get to McMurdo, we should see some processing. Just looking at my notes. We're going to go back, while this is running, I'm going to turn off the ground processing so that we can catch up and move forward a little bit. So ground is turned off. Everything about this is going to move faster. And I'm going to go back to PowerPoint for just a short tour. Just a quick look. I want to show you how I'm actually modeling data, and one of the trades I had to make would be a decision to run this as a discrete event model or to run this as a flow model. A flow model having far fewer events will run much faster and give you integral values that I can't get in a discrete event model. So what's shown here on this chart would be that what I'm recording on a satellite, and this is just 2.5 orbits, 3.5 orbits, is when it's collecting data shown in green during night, during day. You're getting variable rates. So to model just what's going on in the spacecraft for 6 hours worth of simulation, let's see, yes, about 6 hours of simulation, there's only about 6 events, and that would be a great flow model. But adding to that, now we're going to take the data that's in the solid-state recorder and periodically drop it or downlink it to these ground sites are shown here. So I've added another 7 or 8 events. I'm breaking the data up in smaller pieces. And I can still do this in a flow model. And what I'll be looking at in future efforts is whether or not I can move to a flow model or a rate model. after adding rain attenuation data loss. I've shown here data lost in just these sequences shown in yellow, and the data being recollected later at ground site 1 in these 3 segments of data. Just a representation. So I've added another 10 or 15 events. Could still do it in a flow model. What happens in a model where you're actually representing weather algorithms or flow models for whether it's paper products or any other product that oil or otherwise, if you need to know the smallest details on what data is passing through, as shown here, I'm modeling a cloud representation and land and ocean representation. There become tens of thousands of events now to model, and so as shown in the bottom, we're modeling in packets as a discrete event simulation. And this perhaps deviates and takes us away from a flow model. What goes on next, and we'll go back to the ground model, is we're still taking this sequence of information and thousands of events on land and ocean and ground. All this information in packets is being flowed to the ground, shown and represented in the bottom. And we'll go back and look at the model. We have dozens of algorithms represented. We have tens of CPUs simulated in the corner, and we'll go back and look at the animation, true animation of that. So with that, I'm going to switch back to the model. Might be a good time to ask while I do that. Are there any questions, Dave, that you find of interest? We've really looked at orbital modeling so far.
No, I don't see any questions here, Doug. So if you have any questions, type them in, and we'll do our best to answer them.
Okay, so I'm going to turn off animation, and things will run a little faster. While this is going on, we're moving ahead to 300 hours, where we're going to actually lose data in a rain event, but we're going to go to look at the ground segment here. We're going to turn ground on. That'll slow us down a little bit. And let's turn on animation. So up to this point, we've been loading data into solid-state recorders. Those solid-state recorders have been, well, let's just do a subset of that. So what's going on board the satellite recorders is they're collecting data. So they go nearly 3 gigabytes of data, and then they're downlinking data. And you see different size peaks because we're dealing with different data rates. We're dealing with different opportunities to downlink the data. And then what's going on in ground and the buffers in the ground. Let's see, where are we? Try not to get too lost. Is we have a certain level of activity in, we can actually follow packets of data and see where they've come through the downlink into Guam and the different receptor sites. So all this data eventually arrives at the front door of the ground site. So let's go there. Now, actually, I'm going to run it fast for a while and tell you some of the other things we can do with ground. So one of the things that we have a selection when we get to the ground is we can pick different processors. And with those processors, we can, in this model, have the CPU, speeds, the number of processors, number of threads within a CPU, multi-threading. The attributes that are really there in industry can be modeled and selected here at the top level, so that when I get to processing data, what you'll see is a representation of your system, or possibly a system you want to pursue in the future. We'll be looking at a lot of software algorithms. Our software algorithms, you'll see, are represented in terms of what their processing loads are, and we'll be looking at dozens of those briefly. And we also eventually would be looking at what algorithm attributes need to be modeled. Some algorithms can run in multi-threading. Some algorithms need a lot of memory. Some algorithms need a lot of I/O. Those are opportunities to model in a very intelligent way what's going on in the ground system and whether or not you're going to be able to keep up with the surge of data. Remember, we don't have a flow of data all the time. What we have is data that is coming down in surges every time we hit a ground site. And you can see Guam is now cloudy. Anybody you know in Guam, you can let them know. Let's go to the ground segment. We'll be looking at the hardware in a minute, but let's look at the ground processing. This is a representation of what was done for MPOS. We've processed over 23,000 packets of data here. So what you're actually going to be able to see are packets coming through. Well, I don't know why that one's going that direction. Let's hang on a second. Because ground is off. Good point. Once ground is on. Now you're seeing thousands of packets flowing through these models. Another level of representation can be to change the color of the data packets flowing through here, or actually representing whether or not they're information packets or material packets. Everything can be represented as you see the flow of information. Now, many of these algorithm sets are dependent on information to the left or upriver. And that means that the products to the right are waiting for products to the left. And that all affects the latency of what we're producing here as a system. Within these view that you see here, we're looking at land algorithms. These land algorithms, for instance, will only process data when the information or the satellite is over land, and it pretty much ignores when it's over the ocean. So these are not processors. These are not CPUs. These are representation for algorithms. They need memory, they need I/O, they need processors. So this is mapped to models and representations for the hardware. These represent the algorithms. Lloyd, I know you're probably on the line, and Lloyd Matthews worked with Lloyd at Northrop Grumman on similar work for MPOS. Would recognize some of this work we did for NASA NOAA. So with these algorithms running, they need resources. One of the resources we're modeling here, let's turn off the line animation, would be I've got an architecture of 4 servers running, and for the most part they're not heavily used, but we'll go look at their utilization in a minute. We can run them round robin. You could do them in a random distribution. That may not make sense, though, when you need contiguous data or sequential data processing. Regional, where are we looking? Maybe Asia, weather needs to be processed differently from CONUS weather, or spacecraft specific, or some sort of prioritization scheme. So it is for you as a developer to build into the allocation of your resources enough schemes that you can pretty much stimulate the thinking of your customers. And this has been the case working with NASA, NOAA, and the Air Force. So you see that they're running 100% and they're backlogged. And that may or may not be a problem if it's not too long. And what you should get in a case like this would be computer utilization. You recall I turned it off earlier. Let's just look. So we're looking at a very dynamic architecture. Data comes, it goes, it's collecting a variety of land, ocean, and cloud information. All these things are dynamics that drive ground processing, that drive the capacity of the system or the loading of the system, and it very much drives what goes through the data communication model. So is it still a model that can be run with flow and rate library? It's something I'll be looking at, and something that I looked at a couple of years ago with Cecile. But this shows it's a very dynamic ground processing, ground loading model. And at the end of the simulation, you'd be able to tell your customer whether you lost data, whether you met specifications in terms of late data. With weather data, we try to produce the most current data, and yesterday's weather is of no value. All right, I'm going to... Are there any questions so far?
Yeah, there's one comment that he said it didn't look... there's a comment from someone who says it doesn't look too random.
That's a good point. It came up at conference. The land ocean will not be random. The weather model in Guam will be random, and your cloud model and overcast model could be random. So what drives your ground is a choice. And if it's average loading for 20 or 30 years, as we've done, you may not need the most random model. But in terms of outages, we have random outages for receptors. And you could have random performance outages on the spacecraft. Certain sensor bands could go down, and that would change your product loading. So it is a very good question that most of what we're doing is not as random. You could change your locations for your remote sites, and these are very costly things to do in real life, and those are great trades to make, but it's not one of a random nature, not a Monte Carlo environment. And maybe Richard or Lloyd would have a input on where we could where the world is random in this environment. But for the most part, you're looking for performance on a fairly static architecture, an architecture that perhaps hasn't been defined yet, though.
And you did get a hi, Doug, from Lloyd Matthews here that I wanted to.
Okay, glad you're on, Lloyd. Yeah, we worked, I'd say 5 years, or maybe it was 10. No. So what we're looking at on the ground and what drives these algorithms are the, in just this model, is whether it's a day-night, because certain algorithms are not going to run as well and they take more processing resources, and whether or not it's land-ocean. I don't have a model in there right now for clear and cloudy. So it is about representing in this model what goes on in the weather environment. For other Air Force projects, we have modeled other events that will drive the system in surges, that will drive loading in surges, and it's an environment that can be randomized in that case, but not one I will have time to talk about here. What we're looking at is how long it takes to produce a product. And early on in the model, you can see that we had the latency is usually around 50 minutes. Every orbit at this altitude of 850 kilometers is about 100 minutes. All our latencies, including processing, are around 50 or 60 minutes, except when we broke McMurdo, and you see it dropped up, it rose to like 90 minutes. And we're going to lose some data pretty soon, and you'll see that it takes a number of orbits to collect that data. So it is about latencies. And I'm going to speed it ahead until it comes to a stop, and we're going to a rain model. While it's doing that, and it should stop it on its own, I'm going to go back to PowerPoint. And Richard.
Doug, I do have a question from Lloyd Matthews. He asks, is Guam the only receptor being used for the NPP, or is more of safety net in place?
That is an imposed future that we were looking at. Guam was one of the things we considered. MPP, I believe, is still only using 2. Actually, it started off with only 1 spoil part. And they were talking when I left the program to bring in McMurdo for the weather capture would cut latency from 100 minutes down to 50 minutes, obviously. So it's, I haven't heard anything about other imposed ground sites. We were looking at 15, I believe, worldwide, and latencies down around 15 minutes. It meant you knew your weather before you had your weather. It was a very good system. And for recovering data, data was always available not only at primary receptors, but and secondary, it was scattered throughout the world. It was a good system. What you should have on your screen now is just a small piece from the paper and from the presentation. And Richard, if you're there.
Yeah, this is Richard again. Just going back to what we were originally talking about, the rain attenuation effects. We realize maybe perhaps most of you, if not many of you, will be looking at rain attenuation effects or even satellite systems, but just to give you a background on how we approached our model here. For the rain attenuation effects, we looked into various rain models. There's something called Crane, there's something called Flavin, there's also ITUR, which was the main basis for what we looked at. And when we looked at some of the ways of quantifying that, basically it all comes down to the idea that you have the factors of rain rate, obviously how much rain you get going on there, as well as elevation, excuse me, elevation angles, and consequently your slant range, because your slant range is going to be dependent on that elevation angle. We looked at anything above 5 degrees elevation as being reasonable. Below that, you're looking fairly horizontally, and you're going to get ground obscuration or other effects. But for above that, you can see, if you're looking at the chart here, how your most favorable condition is when you're directly above your receptor site there, where you have the smallest amount of atmosphere to cut through. It's just straight up and down, and you can consider it about 100 or even 130 kilometers altitude. That's your most favorable condition to getting into getting your communications. Now, if you look at the 45-degree elevation angle, you look at that. Doing your simple math, as we all remember from our sine and cosine functions, 0.707, and you end up getting 41% more atmosphere to cut through when you're looking at a 45-degree angle, going down all the way to 30, getting about twice as much, and so on. We're showing basically what's a flat Earth approximation. Obviously, there's curvature effects, so you get a little cutoff on that, but you get the idea there that the more atmosphere you have to look for, the more atmosphere you have to look through, rather, the more attenuation effects that you're going to get from the rain and such. So that is the basic overview of our rain attenuation as it affects our data loss. And again, obviously, we know there's other things other than rain attenuation effects that are going on there, including possibly jamming or EMP or solar flares and such. And if anybody does have any more questions about that, the satellite toolkit stuff especially, which is my forte, feel free to ask or contact me. I'm happy to consult with you on that. And but that should give you a pretty good overview of the rain attenuation there. I think, Doug, it's back to you.
Yes, thank you, Richard. Richard did all this work gratis for STK for this presentation. He had time available, and I think he still has some time available. If you want to get a hold of him, we'll have contacts at the end of the presentation. This chart in the upper right hand, it shows that we're going to be looking at a couple of situations where the orbit takes us, and it's a glancing blow off of Guam at 5 degrees, maybe 5.5 degrees. We're going to get maybe just 2 minutes worth of contact, and it's in jeopardy if there's any rain, and that's why we'll be going back to the model, because there will be rain as promised. But if it comes straight overhead, 90 degrees overhead, you're going to be looking at 5 degrees on each start of contact, end of contact, and if there's any rain, you're going to lose data at the beginning and at the end of each contact. And we'll be looking at both of these cases in the model, and this is the captivating portion of our presentation that was given at ExtendSim, trying to make rain interesting to a large number of college students. Let's see. I'm not sure I can go to the next chart without getting away from my pen. Okay, the other mention of rain is to model it on the ground. Richard has captured whether or not we will lose data if we have rain. The way we modeled rain, shown in the lower right, we had 10 or 20 years of rain data for Peterson Air Force Base in Guam. And to model it, you have to have series of rain days and series of dry days in a realistic, a representative fashion to show rain so that you can lose data. So going from there to the upper right-hand corner, statistically analyzing that data for significant rain days, we were able to plot whether or not we would have rain in blue, 50% probability of only one rain day, with something like a 28% probability that you would have 2 rain days, and then it diminishes. The same is true for dry. We were looking at the number of dry days, far more long dry days, but it was therefore a profile that would tell us in our model whether or not it was a rain day. And if it was a rain day, then we had the historical information shown in the lower left. If it was a rain day, it was usually 50% of the time 10 millimeters of rain or less, shown all the way up to 130 millimeters in certain cases. But this is only for the day, and we needed to know what the hourly rate was. So we took other meteorological information that's available, and that is properly cited in the paper. We looked at then blocks of rain, and this is all the information you get as a 6-hour block, to come up with what might be hourly rain over a 6-hour period of time. This drives the model. Now we have rain rate. From Richard, we have elevation angle. And from the calculation of rain attenuation, we get data loss and determine what portions of the orbit down around the horizon we're going to lose data. So I believe we'll come back to this in a minute. Let's go look at the model. And if things have worked correctly, we are going to turn on some animation. The ground is still on. We're paused just at this point in time. Try to remember where we are. We're going to run this until we get to a rain event. And the solid-state recorder has been modified to show rain and loss of data. So that's kind of nice. And we'll go in and look at the model for Defense Weather Satellite 2. So I'll start this up again. We've got satellites 1 in yellow, 2 in red, and they're passing through Svalbard. Things are working properly. Watch red. Spacecraft 2 is filling up with data. Goes through McMurdo, drops its data. Shortly thereafter, first DWX-1 drops its data. Okay, as we see, DWX-2, the second satellite, is just clipping Guam. At this point, it has already lost, shown over here on the satellite recorder, data shown in black. This data is going to flow through the system. It isn't until it gets to the ground that we realize the data is lost. And that's because we're modeling autonomous receptors. We do not have somebody sitting at Guam sending out a signal saying there's no rain and it's okay to send data down. This data is lost, and if it isn't often, it's cheaper to lose the data and recover it than it is to put somebody at the site at full time and monitoring and commanding. So we're hitting Guam, and you see we're starting to lose this data. We had a full buffer, and it's still got some data in it. And as we go forward, Guam, you see in the bottom center, is showing rain, and I'll pull up the plot a little bit later. So as we go forward, I believe we're going to see everything in that buffer will go to black, and it's going to stay on the spacecraft until it's overwritten in the next 2.5 orbits. So we have to get that data off before I lose it. So at this point, the second satellite, red satellite, is hitting Svalbard. It thinks it has downloaded all the good data it could at Guam. It doesn't know about the black data, and it's going to clear its buffer in Svalbard. That's the northern receptor. It's shown over here, Lapland, and all its coverage over the North Pole is represented by this red contour at 5 degrees elevation angle. So here we get there, and it's cleared its buffer. We still have 2.5 orbits to get the data off of it, shown in black. So let's hope it happens. So we're coming around. Red satellite is just leaving Svalbard, shown over here in the Mercator map. Where my cursor is, it's just leaving McMurdo. It's going into ground processing. And as it passes through the Atlantic area, South Seas, we're filling the buffer, getting to McMurdo. It's clean. We still have this data on board, and we stand a chance of losing it. And now we're collecting data coming to Guam. Now, we still have rain in Guam, and I can tell you that we're going to lose data in Guam. It's going to pass directly overhead, but we're not going to lose all that data. We're losing data up to something like 5.8 degrees because of the rain model and how much rain is going on there. So you're going to see this black data, and we're going to collect some more lost data. This is an excellent representation of hundreds of data points in the system. Each one of the columns in this satellite recorder, I've sized it to be 1 minute's worth of collected data. So we're looking at maybe 30 minutes of data loss and another set of data. It's lost data twice over Guam, but now we've come to Svalbard. Red satellite is just reaching the boundaries for Svalbard and red, and if the model is working correctly, it should reclaim the data that was lost in the first contact. Let's watch that. It's always amusing to see what makes engineers exciting. So I apologize. We have collected the data that was lost an orbit ago, and when we get to our statistics, it will show that it collected at least 100 minutes worth of lost data. Here's the red satellite. It's coming up again. It's not going to hit Guam, and it will be collected eventually and recovered at Svalbard. You'll watch the black go away over here on the right, and away it goes. So what's of interest in this model may not be of interest to everybody on session here on the phone. But what can be of interest here is the fact that we are representing a lot of complexity in a place that shows your customer a orbital setting, a ground setting, what's in the spacecraft, what the values are in the spacecraft, whether these are representations for product flow and distribution in other commercial industrial models. Something like the color map will be of great use in showing thousands of elements and what their current state are. So the model will continue running. I'll have just one more thing and we'll go back to our presentation. The only thing I will show you is the plotter. These are the latency, the product. Everything in blue these are hundreds of individual packets, and you can see that they've collected another 100 minutes worth of latency in their loss and in their recovery. And we know where that data is, we know why it was lost, we can look at variations on saving that data, but as pointed out, it's not truly dynamic except to do, over a 30-year period, a lot of random rain. I'm going to take us back to the, no, we've seen all the charts. Are there any questions that have come in, Dave?
Yeah, a couple have come in. Are you using version 9 or 9.1 for this?
This is 9.1, and I don't think there's any difference. Everything I have here runs in 9, of course.
And then the other question is there information available on how you imported the data, or how you integrated ExtendSim with Satellite Toolkit?
Not in the paper per se, but suffice to say that if you have used the model and you've used databases, there is the ability to, in your database managers, which I keep around, to import data from Excel spreadsheets. The Excel spreadsheet was a product of STK, and so we're importing a lot to do with orbital information and the product that we produce. Anything else? So there's ways to go. This work is not complete, and that should ring true with anybody that's done simulation. We're not done. We never are done. But one of the things I'd like to do is move towards using the scenario manager that's in the current version of 9, possibly 8, of Extend. And that would, if I stop the simulation, are there any questions on the simulation? Oh, let me see. I never went into the code itself. Behind every one of these hierarchical blocks are a lot of blocks. How they could be put together, there are 100 variations on how this could have been done. For me, it was modeling the contents of data being generated by the spacecraft. When would I lose the data shown in blue? How would I recover that data? And all that can be modeled 100 different ways. But this has some very special effects that were for the IMPOS program.
Doug, there's a couple more questions that just popped up. How are you getting algorithm latency versus WX data now? Has it become more accurate since NPOESS?
Okay, how are we getting latency data now in the real world? Actually, Dr. Foda may be even on the line. He's on MPP program for NOAA. How they're getting data is they're getting at least 1, possibly 2 downlinks of large volumes of data every 100 minutes and processing in a pipeline very much like shown here, which was all collected from public available information from the IMPOS era. What was the second part of that question?
Has it become more accurate?
Everything about the MPP satellite is producing far more quality data than has ever been produced. I suspect that's not the question. It is more accurate in terms of what is really going on in weather. The most most views of weather you're seeing right now are coming from the GOES program, which are geosynchronous satellites, and they're a constant view of cloud cover. But this information is giving you information on ice and from the MPP program, not this simulation. From ice to land to ocean currents, probably the most critical thing we need to understand what's going on in our ocean currents, because they determine the weather and the energy of the weather around the world.
Okay.
I'm pretty sure I missed what that question was.
This is Lloyd Matthews asking the question. Just asked, since since you and he were working on this, is it more accurate now?
No, this model has no information on what the algorithms really are doing.
The other question here is, and I think I know the answer, but I'll let you answer it. So SDK is writing to a spreadsheet, and ExtendSim reads the spreadsheet.
SDK can either write to a spreadsheet or certainly to a text-based log, comma-separated log, probably a number of options, and Richard, you can correct me, that is imported into Extend. To communicate with SDK.
Yeah.
Mm-hmm.
Yeah, I was just going to say we can export data in various fashions, and I believe too there's a way of even using SDK sort of in an interactive fashion there in a real-time fashion. And I think you or Dave might know more about that too, about how previous interactions between SDK and ExtendSim, but I know that's been done too.
Well, I can almost hear Lloyd jumping up and down. Lloyd was responsible for building the interface to SDK in the IMPOS days, and that was in a TCP/IP, packet-based information, message-based interface, where SDK was getting constantly information on where the spacecraft were and whether or not they could see ground sites. And we not only did that on a wonderful 2D display, but we went to one of the meteorological conventions and did it in one of the 3D globes, truly interactive simulation with driving SDK with information. Any other questions?
Yeah, no, that's the questions I had.
Okay, if you wanted to post any other survey while we ramble on, there was one just to find out if there anybody out there that is new to Extend. I'm sure this cracks an area of Extend most people don't know about, and that is data communication, orbital, space, and ground processing. I've never really done manufacturing and distribution, and it's very good for that, and I've seen Robin Cook and a number of our advisors do excellent, exciting things with it. One of the things in this model that I have is I'm exporting all my results to spreadsheet at the end of every run, and I need to start looking into this scenario manager to do that for me, but it's one of the ways I did it early on over here. I guess with that, let me put in just a word for Richard and I'm still involved with the government. Some of this work has been done for the government. Some of this is available for government work. Richard has supported me and is available for contact and would very much like to support anybody in the SDK and system engineering arena. We're both happy to entertain any future work. We're with GreenDart. There's a phone number. There's our phone number. If you didn't enjoy what you saw today, then remember our number is 555-1212. But if you did like it, there's the number.
Doug, the result of the poll is showing right now, so I'll bring it back once people have had a chance to look at it.
Okay.
Are you familiar with ExtendSim? Is about half people here are use ExtendSim often, or maybe 2/3 use it often or occasionally, and we've got some people that don't use it or was unaware of it before the webinar. So.
Before we log off, I would ask those in the manufacturing and industry area to post, if you would, how something you heard today might be of interest to manufacturing. It really blew my mind that we could offer something that industry is outside of satellite communication interested in. So please post it as a question. Dave gets those. We'll see them later. It would be a real interest to us.
And Doug, just to follow up on the Doug, I mean, obviously from the winter sim, I'd say one of the things I was truly impressed by was how much modeling and simulation comes into all kinds of realms of industrial engineering and other types of applications. So we realize there's more obviously going on out there than our domain expertise, but this is just a sample of some of the things you can do with it.
Mm-hmm. So with data communication, that's one of the largest crossovers. How are people pushing data packets around and whether or not they're using flow models? Did you ask the question about flow model?
I have not. I will post that up there now.
Oh boy, we can definitely kill them with surveys. Love it. Thank you everyone for tuning in. A large number of you we've met. We appreciate your patronage. And thank you, Artie, for watching out for Richard and I. Dave, thanks for inviting.
Well, thank you very much, guys. This is good. We're getting our answers in here for this, so I like this. This got answered pretty quickly. So let me close this and share it. And it looks like they're based on the numbers here. Probably one or two people have used the rate or flow library for communications modeling, and that'd be a real interesting thing to talk about. So whoever answered yes on that, it'd be interesting if they came forward and we could talk about that. I know Doug has particular interest in that. So.
Yeah, I was hoping there would be a few people interested in just that rendition, that viewpoint, that perspective on flow versus discrete event. It's a challenge. It's a question whether or not you can do it in flow model because it is clean. It is the best representation of data flow. But then you have attributes.
Well, thank you very much, Richard and Doug. Really appreciate your time putting this on. Are there any other questions here? We got just a couple minutes to go here, but if not, we'll end the session. Our next session, we're going to skip April, and in May we're going to have our own Anthony Stasi talk about reliability modeling. So this should be an area of broad interest to a wide variety of people. So that should be a good presentation on that.
And Dave, thank you very much for your support too.
Oh, well, thank you guys. That's what makes this whole program work, is bringing people in from the outside. And if anyone who's attending here would like to do a master class, feels that they have something that would be in the interest of other people, please contact me. I really like to bring in new people and new ideas, kind of show off what you've done. That would be just great. So, okay, I think I don't see any more questions, so I appreciate your guys' time. We'll see hopefully many of you back in May when we talk about reliability modeling, and I'm going to end the webinar now. Thank you again.
Okay.